Hello again. Now we are going to move into the next topic of data cleaning, which is outlier analysis. First, we need to talk about what we mean by an outlier. For now, we're only thinking about one variable at a time. And the idea here is pretty simple. There are extreme values on that variable. The question is, what do we mean by extreme? So, extreme doesn't just mean very large or very small. It means very large or very small with respect to the majority of the data on that variable. So, if we're thinking about the data on the variable in terms of a distribution that represents a population, then these values are very unusual with respect to that distribution. So much so that we essentially conclude that they are invalid, that they do not come from the population that gave rise to our putative distribution. So here are some examples of potentially extreme values. A human height measurement of 3 meters. This one is both extreme and, as far as I know, also illegal. I don't think there's ever been anybody who is actually 3 meters tall. High temperature in Utrecht of 50 degrees. This would be extreme, but perhaps not illegal. Maybe it could get that hot, but that's definitely not going to happen in any normal circumstance. Or the income of a student being 250,000 euros a year. Extreme, definitely not illegal. There are very fortunate students who maybe pull in that much money every year. But this would definitely be different from your standard population of students. So this would be a very exceptional case. Now, one thing in particular to note is, for the time being, we are thinking about these values only in terms of the data and not with respect to any given model, assuming you don't want to take like a really liberal view of a model and say that, the marginal distribution is a model. So in that sense, we are thinking about these in terms of like an intercept-only model. But we're not thinking about outliers here in terms of like model diagnostics. We're going to come back to that later. So after we discuss linear regression, we will discuss assumptions and diagnostics. And part of that procedure, basically the procedure of checking that your model results are trustworthy, is looking for influential cases, of which outliers are one particular flavor. So this concept of outliers will come back again. But for now, we're just thinking about extreme values with respect to the data itself, or themselves. All right, as I said, a univariate outlier might be an illegal, impossible value, or it might not be. One of the most common ways that you run into outliers are data entry errors. So if you had any human in the chain, then sometimes there was an error mistyping values, for example. So this used to happen a lot more when questionnaires were administered with pencil and paper, and then you had exhausted, hungover undergraduates transcode that data from paper into a database. It's very easy to hit the 5 key twice, and then what was supposed to be a rating of 5 on some kind of Likert scale ends up as 55. So that kind of thing happens a lot. That's a very common source of errors. Also, in terms of human error, if you make a mistake in your data processing pipeline, so if you write some code that's supposed to convert, some kind of weblog into some kind of numeric data, but you have some bug in that code, then that can also make outlier values, extreme values, also due to human error. But what is also completely possible is that the outliers are accurately recorded data that represent real experimental or observational subjects but are still too extreme. So it doesn't have to be an error. It might just be a crazy extreme case. Obviously, it's easy to think about this in terms of income. I find it easiest to think about this in terms of income, perhaps a bit betraying my cultural heritage. Wealth disparity is not exactly a small issue in the US. But if you were to take, for example, a US population, and I imagine also most European populations, and you just naively plot a histogram, for example, of the income of every person in that country, it's going to be very, very severely right skewed, in the sense that you're going to have quite a lot of people in the kind of lower working class, middle class, upper middle class kind of range. And then the tail is going to dramatically thin out, but you're going to keep having entries that go higher and higher and higher and higher. So obviously, if you have Jeff Bezos in your sample, there's going to be some data point way, way out in the tail that has just a ridiculous annual income, right? That doesn't mean that it's illegal. He just pulls in a ridiculous amount of money every year. So that would still probably be an outlier. The question we have to ask ourselves then is, does this data point arise from the population that I am trying to analyze? Does this data point arise from the population to which I want to generalize my findings? If the answer is yes, it's not an outlier. If the answer is no, it's an outlier. It's a very simple decision rule, but it's not so simple to answer necessarily. So it can be difficult to decide whether somebody does or doesn't belong in your population, right? So that's this is the key distinction, right? So Jeff Bezos is a valid person, presumably. Maybe he's a robot, who knows? But and his income is valid, right? That's how much money he actually earns. But if I'm trying to make inference about the general U.S. population, maybe I don't want to include Jeff Bezos, right? Maybe if I'm trying to tell some story about how your work situation relates to your quality of life or whatever, then Jeff Bezos isn't part of the population that I care about, because his work situation is so damn weird that it doesn't apply to the story I'm trying to tell. So in that case, I would exclude him. He's an outlier, not part of the population I'm trying to generalize to, and that's totally fine. But if I did want to, for some reason, make a truly representative statement about every single working person in the US, from the highest earners to the lowest earners, then Jeff Bezos would not be an outlier, and I'd keep the data. But then I'd have to do some really weird analyses to deal with those extreme scores, because they will break the hell out of something simple like linear regression. All right, well, let's get into our recommended screening procedures. Here, I want to talk a bit about the box plot method, which is what I'm going to call it. It goes by various different names. I'm going to call it the box plot method. And the idea is very simple. We essentially take the box plot and we find these cases up here. So when you generate a standard box plot, you're generating a plot based on the 5-number summary of the data. So we have the median, the 25th percentile, the 75th percentile, 25th percentile, and then these outer fences, the lower fence and the upper fence. And these are generally defined as some multiple of the interquartile range, where the interquartile range is the width of this gray box. So the By default here in this box plot, these are 1.5 times the interquartile range. And then any data value, any observation that falls outside of those fences is considered a potential outlier. It's considered extreme according to kind of Tukey's original ideas. So this whole box plot idea was proposed by Tukey in his 1977 book just called Exploratory Data Analysis. He was the one who kind of came up with this box and whiskers plot and showed how you could use it to flag outliers. Now, one of the reasons, or some of the reasons that this is a really nice approach is that there are no distributional assumptions made about the data. It's just a straight up summary of the order statistics. So the relative ranking of the observations. You don't have to assume a distribution. And it's not sensitive to outliers itself. Right? So the box plot has a very high breakdown point. I would encourage you to think, what is the breakdown point of these 5 number summary? So of the box plot, the 5 is going into the box plot. So if you would like, go ahead and pause the recording and think about it if you don't know it off the top of your head. So hopefully you thought about it, and hopefully you came up with the answer 25%. So we can replace up to 25% of the data with arbitrarily large contaminants, and we'll still have an accurate box plot, an accurate 5-number summary. And the reason for that is the first statistic that we actually need to be able to define is the 25th percentile. We need to be able to plot this bottom edge of the box, or the 75th, if we're thinking about it in terms of large, arbitrarily small values. But as long as we don't replace more than 25% of the data with contaminants, then the 25th and 75th percentiles will still be defined. Of course, the median is still defined. So the interquartile range is still defined, which means the whiskers are still defined, which means the box plot still works. So our breakdown point for the box plot is 25%, which naturally is not as good as the median at 50%. But honestly, if you have more than 25% contaminants in your data, I think you have a bigger problem. I think if you're labeling more than a quarter of your cases as outliers, then you're probably thinking about your population entirely incorrectly. Something has gone wrong with your measurement. All right, so to actually sort of calculate this idea, we have to define these fences. So we define the interquartile range, which is simply the 75th percentile minus the 25th percentile. Q is for quartile, first quartile, third quartile. And then the lower fence is going to be the first quartile, so the 25th percentile, minus some weight times the interquartile range. The upper fence is the third quartile plus some weight times the interquartile range. And we generally used either 1.5 or 3. These were the rules of thumb introduced by Tukey, and he basically said if something is bigger than 1.5, if it's bigger than 1.5 times the interquartile range, then this is sort of a possible outlier, although he didn't use that exact language. If it's bigger than 3, then it's a probable outlier. Right, so those are cases to think carefully about. It's relatively straightforward to implement this idea in R. There isn't a nice single function that I've been able to find that just kind of flags outliers based on this box plot information. There is a package called Outliers that kind of has that capability in it, but the problem is it totally breaks down with missing values. It doesn't accept any missing values, and when you have missing values, the way it deals with it is not particularly good. So that's not really a viable solution for us, as we rarely have a fully observed variable that we're trying to screen. But thankfully, it's pretty straightforward to kind of do this ourselves in just a couple steps. So the key thing that we can use is the boxplot stats function. Of course, if you want to, you can just calculate the quantiles yourself using the quartiles function, and then compare the data to the quartiles. Like it's easy enough to do, but we can make it one step simpler. So if you call boxplot stats on a data set, you give it the weight, so the C that you're going to use to weight the interquartile range. Here we're going to go with 3. This will calculate essentially all the statistics that go into making this plot. I mean, it's the back end of this plot, basically. And one of the things that it calculates for us are the outlying cases. So this out field in the list that we get from this boxplot stats function contains the values of all the outliers. So this is a bit unfortunate. Like, it gives you the values of the outliers. It doesn't tell you which cases these belong to. The reason that it does that is because indeed this is the back end of the plotting function, and to plot these things we need to know their values. So that's the useful information for plotting. For screening, it would be nicer if it gave us the observation number, but of course it's not a terribly difficult thing to find which observations match these cases. We just have to use a logical comparison. So we're going to do that here by checking which of the BMI values are in these out values here. So out is going to be this numeric vector that has the values of the outlying observations. The in operator here, %, in, %, this is an infix logical test that says which of these values are in this vector. And it's going to return a logical vector with the length equal to the first argument. That's true for any occurrences here that also exist here, and false otherwise. So that'll give us a logical filtering vector to basically find the rows in BMI that are outliers. So we supply that filtering vector to the which function, and we get the row numbers. So we see that observation 574, 668, and 733 are the outliers that were flagged by our boxplot method. And again, we can use that index to grab those rows. So you see, again, it is the very overweight boys that are the outliers. When we're dealing with outlier analysis, one thing that we need to be very mindful of is the sensitivity that our statistics may have to outliers themselves. Certain statistics that we use to detect outliers are themselves very strongly affected by outlying values. That's the reason that using a standard Z-score to detect outliers isn't a very good approach to this problem, because the Z-score is too sensitive to outliers. Now, the way that we make this concept rigorous is with the idea of a breakdown point. So this is a really useful statistic, and I find it quite clever, quite fun to think about this. The idea of a breakdown point is to try to quantify the extent to which the data can be contaminated before our statistic breaks down, before it fails, essentially, right? So there's various ways that you can make this rigorous. Some definitions talk about the number of contaminated cases you can have. Some talk about the proportion. The way that I'm going to define it is as the minimum proportion of cases that must be replaced by infinity to cause the value of the statistic to go to infinity. Okay, I'm picking infinity here because it's just the most extreme form of contamination we can have. But you could also say the minimum proportion of cases that need to be contaminated to also invalidate the estimate of the statistic or something like that. But this is a more mathematically rigorous way to define it. All right. And yeah, so here now we can see why we have a problem with our z-score, because the mean has the worst possible breakdown point. The mean's breakdown point is 1 over n, which means if you replace even one value with infinity, you'll get an infinite mean, right? I mean, that shouldn't be surprising. The mean is just defined as the sum of all of the values divided by n, and obviously anything plus infinity is infinite. So basically, as soon as you contaminate one value, the mean is contaminated. It's absolutely not robust. There is a concept of a deletion mean, or a leave one out estimate of the mean. There's a whole class of sort of leave one out diagnostic statistics that we're going to come back to when we get into model-based checks for like outliers and such. The deletion mean is really going to come into its own. And the idea of the deletion mean, or any kind of a leave one out statistic, is essentially if I'm trying to evaluate, say, observation 5 for outlier status, then I'm going to calculate the mean using all of the other data, but leaving out observation 5. So that if observation 5 is an outlier, it can't mask itself. It can't contaminate the estimate of the mean. So this method will be robust to one outlier, but it's robust to only one outlier. So a leave one out statistic like this, for example, the deletion mean, has a breakdown point of 2 over n, which means that we can replace one value with infinity and it won't affect the estimate. Specifically, if we replace the value that's being tested with an infinity, we'll still get a valid estimate of the mean. But as soon as we have two outliers, so if we replace two values with arbitrarily large contaminants, then the mean breaks again. So this is one step better than the mean itself, but it's still not awesome. The median has a breakdown point of 50%. So this is why we use the median to summarize central tendency when we have poorly behaved distributions, like if you have a really skewed distribution. This is insane. So to make this more concrete, we can replace anything up to, but not including, n over 2 of the observations with infinity, with an arbitrarily large number, and the median will not change. It will still be the same value that it would have been if we didn't contaminate any of the data. That's insane. That's a ridiculously robust statistic. It seems almost impossible, but it works because of the way the median is defined. The median doesn't aggregate any data. All you have to do with the median, to calculate the median, is to sort the data and then find the middle case, find the middle value. So when you sort the data, obviously anything that's infinite is just going to go to the top. You're just going to have a clump of infinite values. But as long as that clump of infinite values doesn't exceed half of the data, then the middle point is still not infinite, and it's also still the correct middle point because it's the largest of the finite values, but that's still the correct median of that variable. So the median actually has the best possible breakdown point. You can't have a breakdown point more than 50%, because by the time you get above 50%, then, I mean, essentially you don't have, then your finite points become the outliers, right? Because now you've contaminated more than half of your data, so the contaminants are actually the true values, and the question doesn't even really make sense anymore. So various ranges of robustness that we can have here. And the reason this median can come into the argument here. There is a popular method of screening for outliers called a Hampel filter, I believe, which essentially replaces the mean in the z-score with the median and the standard deviation with the median absolute deviation. So you get kind of a z-score style statistic with a 50% breakdown point. So now we're going to dig a bit into the practicalities of doing these outlier screenings in a real data analysis. So one question that comes up a lot is, can I have outliers on a categorical variable? And more often than not, this actually doesn't come up as a question, but just an assumption that it's not possible. Because I think there's quite an ingrained bias that no matter what we say, an outlier has to be any legal value. So a scale that can only take fixed discrete values can't have outliers. Because, if your scale can take the values 1 to 4, you can't have a value more than 4, so you can't have an outlier, right? Whereas a continuous variable could be, mostly 1 to 4, but then you have another one that's 20. Maybe 20 is an outlier, right? But that's not the case, right? We covered this already. An outlier isn't an illegal value. It could be, but that's not the definition of an outlier. If it happens to be illegal, that's incidental. So it is possible to have outliers on categorical variables because it's possible to have an incredibly unlikely response to a categorical variable. A categorical variable represents a grouping. It's a random variable. So it has a representative response pattern and it has an unusual response pattern, right? So you can have outliers here. Now, the one thing that's kind of unique here is oftentimes if you do have outliers on a categorical variable, that finding doesn't actually indicate bad observations, but it's kind of an inverse, like a reflexive indication of a poorly performing variable. And I'll show you why in a moment. The reason that this is kind of the case is because that if we're only kind of restricted to a small number of response categories, like an ordinal variable maybe takes values 1 through 5, which is like a Likert type rating scale, then to have an outlier on such a scale essentially means you have to have data clustering in one part of the scale, and then you have a few cases that fall outside of those clusters. But if you only have 5 possible response categories, and you then have clustering on top of that, that is severe enough to make the non-clustered items look exceptional, then probably what you have is like a very badly performing scale with like weird floor effects or something. Okay, so if we have an ordinal scale, and for example, most of your sample responds in levels 1 or 2, but then you have a couple people who are responding at like 3 and 4 and 5. Those people responding at like 4 and 5 are probably flagged as outliers. Likewise, for a nominal variable, groups that have a very low membership will be outliers. Right, a nominal variable is literally just representing groups. So fringe groups that have very few members they end up as outliers in the data set. And then for binary items, it is possible to have an outlier on a binary item, but this is almost by definition indicative of a broken variable. Because to have an outlier in a binary item, essentially you have to have basically everybody endorsing one of the categories. Like everybody has to fall into one of the groups, except for a few cases that fall in the other. And then essentially what you have is, in reality, a constant with a little bit of contaminating noise. So That's what I mean when I say that these outliers can exist in terms of the technical definition, but oftentimes they exist because the variable itself isn't behaving well. So like in this binary case, you don't have a binary variable, you have a constant variable. In the ordinal case, you have like a really strong floor effect where basically everybody's bottoming out the scale except for a few people at the top of the scale. And then in the nominal group, in the nominal case, the outliers are like fringe groups. So oftentimes the solution here isn't actually to exclude the outliers, but then just to not use the variable or reconceptualize the variable, think about a better way to quantify what you're trying to measure here, like to avoid floor effects or something. Yeah. But you can indeed have outliers and categorical variables. So what do we do if we find these outliers? Everything we've discussed so far has dealt with the location of the outliers, and we haven't really talked about how to treat them. But they should be treated. So the whole purpose of finding these outliers is that they mess up our analysis, right? So an outlying case is extreme, and it's going to pull estimates toward itself. Right? So we talked about this in the masking discussion earlier, but that same principle of like masking when we're using a z-score also happens if we're estimating a regression model, for example. An outlier is going to pull the regression line toward itself and make the estimate look stronger or weaker, depending on where the outlier lies in the distribution of the outcome. Right? So we should do something about outliers. And here I'm talking about like confirmed outliers, variables that or observations we've decided definitely are outliers. They definitely do not come from the population we care about. Those are the ones we need to deal with. So first off, there's one class of outlier that's the decision is easy. If you have true errors, so outliers that are caused by data entry errors, malfunctions of measurement equipment, broken sensors, whatever. I call these error outliers. Like they're literal errors that cause the data anomalies. These you just fix. If you know what caused the error and you can kind of reverse engineer the correct value, then just do that. Otherwise, just get rid of the outlying data. Now, for non-error outliers, so these are outliers that sort of get flagged as outlying according to our screening or our testing or whatever, but they are still valid data. So it's still like sort of somebody's valid response, but it's just an extreme response. These we can't necessarily treat so blithely. We don't just naively throw them out and pretend like nothing happened. We probably do want to exclude them, but we do that based on the justification, not that they are a mistake, but that they are valid data from a different distribution than the one that we care about, from a different population than the one that we care about. And oftentimes, if you're going to exclude these cases, you want to do the analysis twice, once with the cases in and once with the cases out, just to see how sensitive your results are to that change. And if they're not that sensitive, that's great. That means that these outliers weren't really that much of a problem. You can go forward with your inference, still probably using the results from the reduced sample where you threw the outliers out to use that for your conclusions, but you don't need to worry too much about it. If the results are very different, then you need to acknowledge that, and still you probably base your conclusions on the subsetted sample, but you have to kind of acknowledge that caveat that your sort of researcher degrees of freedom in terms of excluding those cases has had a substantial impact on the conclusions. And maybe if somebody else did the analysis with a different sort of decision criteria for the outlier cleaning, they would come to a substantially different result. Incidentally, there's a totally cool kind of flavor of analysis called multiverse analysis that attempts to quantify this idea of researcher degrees of freedom. So when you're trying to do these kind of subjective tasks that require just human judgment calls, which come up a lot in statistical analysis, outlier analysis being a really great example of such a task, then rather than just doing it one way and kind of reporting the results with the thing done and the thing not done, you do it many, many different ways. So like you screen for outliers 10 different ways, use a bunch of different criteria, and then you get like, 10 different sets of results or whatever. And then you have kind of a distribution of possible findings based on that parameter, that like researcher degrees of freedom in the decision rules about your outlier analysis. And that's an idea that I find super cool, but it's still kind of really, really nascent, and it's not clear how to best synthesize those results into one conclusion. All right, but at any rate, once you kind of find the cases you need to deal with, the most straightforward way to deal with them is just to throw out the entire observation. You can just get rid of that whole case. And of course, potentially report the analysis both ways. Now, for multivariate outliers, that's kind of the only approach we have in terms of a data exclusion rule, because the multivariate outlier flags the entire case. It's not tied to a specific variable. But for univariate outliers, we're not saying that the whole case is bad. We're just saying that one particular variable in that case is bad. So we have a less dramatic solution. We can just delete the outlying value. So let's say we do the univariate outlier analysis on our boys data set, and we find some univariate outliers on weight, for example, but nothing else. We can just delete those outlying weight observations. And in this particular case, we would also delete BMI because it's defined as a function of height and weight, but that's kind of beside the point of the argument. But then we don't get rid of the whole case. We just add a little bit of missing data, which would amount to the same thing if we were doing our analysis using listwise deletion. But as I hinted earlier, you should almost never be doing that in the real world. You should deal with your data in a more intelligent way, your missing data in a more intelligent way. So the approach that I like to take is if I find univariate outliers, I make them missing. And then when I'm doing my missing data analysis, which for me is usually imputation, I just impute those extra missing values like any other data set. Because basically, when I have an outlier, what I'm saying is, well, this value doesn't come from the population that I care about. So I'm going to make it missing, and then I'm going to impute a replacement. And basically that replacement isn't going to be just the same value that the person gave the first time. I'm going to be kind of transforming that subject's response into a response that conforms to the rest of the data set. So given all that subject's other variables, if they had a normative response on this outlying variable, the imputation model will fill in what that normative response would have been. And then we're good to go. We have data that's consistent with the population we're trying to generalize to. And this isn't guaranteed to work. Maybe you impute an outlying value, and then you're back to square one. But at any rate, it usually is a nice approach. There's also a simpler approach if you don't use imputation, or if you don't do anything fancy with your missing data. you can do something called Windsorization, which is sort of like a kind of trimming. And the idea is that once you delete the outlying cell, you just replace all of those empty cells that you made by deleting outliers with the most extreme legal value. So if we're screening weight, for example, outliers are going to be flagged at basically beyond a certain weight. Like once you're higher than a certain weight, that's going to be considered as an outlier. So we delete all those weight values, and then we just replace them with the largest weight that would not have been considered an outlier. So if anybody who weighs more than 100 kilos is flagged as an outlier, basically we delete all their weight values and we replace them with a constant of 100. This isn't a particularly principled way to solve the problem, but as long as you're not doing it to too many values, it doesn't have much of an effect. And then you're still kind of, the rationale here is that like these should have been extreme cases, and now we're making them as extreme as possible, like within our sort of trimming rule. Like they're taking the most extreme possible value, but in kind of an ad hoc way. All right, now finally, there's another way that we can go about dealing with outliers other than deleting anything, whether it's an entire case or an individual cell. We can leave the outliers in the data set and adjust our analysis to a robust variant that accommodates the outliers. And there are many, many different flavors of such robust analysis. Here we're just kind of giving a bit of a sample of some of the possibilities. So one possibility is just to adjust the objective function that you're using to estimate your model. So you kind of estimate the same model. So like maybe you're doing like linear regression, you still estimate a linear regression model, so you're still modeling the conditional mean with a homogeneous error variance and whatever, but you use kind of a weighted estimation function to downweight the outlying cases when you're doing that. So this is how M estimation works. This is one of the sort of potential weighting estimation approaches we can use here. Another thing we can do is kind of the same idea, but we use a trimming approach. So basically, we trim the outlying observations before estimating the model, but we're still, again, estimating the same model that we originally wanted to. So we already talked about MCD and MVE as ways to kind of get these trimmed estimates, but there's also something called trimmed least squares or least trimmed squares, which I think, if I'm remembering correctly, is essentially just the ordinary least squares where you throw out the extreme cases and y before you do the estimation. In a kind of more extreme approach, we can adjust our model so that we are no longer modeling the mean, which is very sensitive to outliers, but we're modeling some more robust target. So here, the target would be the median. So the least median of squares. So actually I misspoke. So I think here we still define the residuals in the same way. So this would be like an OLS regression. We're still estimating the model in the usual way. We're still calculating the usual residuals, but then rather than taking the mean residual, so the sum of squared residuals and then dividing by the mean, we take the median residual. So square the residuals and take the median of that, and then that's going to be a more robust estimate to optimize. Here, the quantile regression, this is where we're actually changing our objective. So in normal OLS regression, we're modeling the mean of y given x, modeling the conditional mean of y, but we can also model some quantile of the distribution of y. So it doesn't have to be the mean, the usual replacement is the median. So we model the median of y instead of the mean, but you can also pick a different quantile, 75th percentile, 25th percentile, whatever. And that's going to be much more robust. Finally, we can change the distribution that we assume for the outcome data. So this would be the Bayesian approach. So in Bayesian statistics, generally, if you find that you have observations that don't conform to some distribution, your preferred method would be able to apply a distribution that does accommodate those observations. Still, in Bayesian analysis, you can have outlying observations, so sometimes there are just cases that don't belong. But if we're talking about robust analysis in Bayes, usually that amounts to using a distribution that has longer tails that can accommodate those more extreme cases. So the Laplacian and the student's t distribution are two popular approaches. So using those distributions to define your residuals instead of the normal distribution. That's it. That will finally wrap up our discussion of data cleaning. So thank you for hanging in with me. Hopefully in future weeks we get all this done in the regularly scheduled programming.